We have here a sketch of a curve defined by parametric equations. You can immediately see it like it's pretty complicated because we've got a ln sec t going on. Now remember sec is 1 over cos or cos x all to the power minus 1, and you can bring the minus 1 down and make it minus ln cos t. I'm kind of tempted to have that just because it's easier to differentiate. T is between 0 and pi over 2. We've got this curve C, and then we're told that we have a tangent at point P when T is equal to pi over 3. And then we're interested in finding the x coordinate of A. So that is we're going to need to find the equation of the tangent and then where it meets the x-axis. So let's give that a go. Actually, I was about to substitute in t is equal to pi over 3, but the first thing is going to be to find out dy by dx. That's our gradient function. And for this, we're going to need to use parametric differentiation, i.e. the chain rule. And this can be written as dy by dt divided by dx by dt. So dy by dt is going to be, we're going to need to use the chain rule here. Oh, sorry, I'm doing it on this one, aren't I? So I'm going to get minus 1 over cos t, and then times by the derivative of cos t, which is minus sine t. And actually, I'm going to get sine t over cos t or tan t. You might have recognized actually that that is when you integrate tan t, you get this. You may have spotted that. If not, it's absolutely fine. And then dx by dt is going to be 2 cos t. So back over here, we're going to have tan t, and then I'm going to be dividing by 2 cos t. I think it's fine to leave it like that. So when t is equal to, it was pi over 3, wasn't it? X is going to equal 2 sine pi over 3. Now that is the same as sine 60, and you need to know that sine 30 is a half, sine 60 is root 3 over 2. So it's root 3 over 2 times 2, it's root 3. Y, meanwhile, is minus ln cos pi over 3, which means it's minus ln a half. Or actually, even better, ln 2. I mean, I took the minus out because I thought it'd be easy to differentiate, but sometimes you want to kind of bring it back in. And then dy by dx is going to be tan pi over 3, which is root 3. Try and remember that tan 30 is 1 over root 3 and tan 60 is root 3. And I'm dividing by 2 times a half. So these cancel and I'm just left with root 3. Therefore, our tangent will have equation y minus y1 is equal to mx minus x1. So y minus ln 2 equal root 3 times x minus root 3. And in particular, we're interested in where that tangent crosses the x-axis. Remember, that was the point A. We need to show that it is this. Just going to borrow this to get it in the right form. Didn't copy properly, bear with me. Okay, that's where we're heading. So when y is equal to 0, that's when it crosses the x-axis, minus ln 2 is going to equal this, so I can divide by root 3. So x is going to be root 3 minus ln 2 over root 3. And we're nearly there. What we can do is we can factorize out of 1 over root 3. I do that because I can see that if I then times this by root 3 inside the bracket, so that will work, and I'll get my ln 2 over here. Now we can rationalize the denominator times top and bottom by root 3, so it's going to be root 3 over 3 minus ln 2, which is what we needed. So just a little bit of manipulation to make sure we get to the required answer. Good start. On to the main bit of the question. Somehow we've got to show the area of R is equal to this thing here. And what this is going to involve is integrating from here to here. Remember, we've if we found this value here, this one was root 3, and we've just found that that value there is root 3 over 3 times 3 minus ln 2. So what we're going to have to do is integrate under the curve between x equals 0 and x equals root 3, and then subtract this triangle here. Now, it might be worth just finding the area of this triangle right now. So it's going to be a half base times height. The base is going to be the difference between root 3 and that thing from before, root 3 over 3, 3 minus ln 2. We also found the value of y earlier. At this point, it was ln 2. So in fact, I can just add that on. I'm going to put it at the start because I can fit it in. And we could try and simplify that. And I've just realized I've not really left enough room, but I'm going to carry on anyway. So I get a half ln 2, and then I'm going to expand the bracket back out. Actually, they made us write it like this, but it was actually in a pretty good form because it was root 3 minus ln 2 over root 3. So if I'm minusing that, I'm going to be minusing root 3 and then plussing ln 2 over root 3. These are going to cancel. And so I've simply got a half times ln 2 times ln 2 divided by root 3, which is going to be ln 2 all squared divided by 2 root 3. Just realized, and I can see in the answer, like remember I'm going to be subtracting that. It makes sense to rationalize the denominator. So I'm going to times by root 3, top and bottom. And when I do that to the bottom, I get 2 times 3, so I'm going to get my 6. And I can see, like, this is a good thing. I've managed to already sort this term out. The next bit is going to be to find the integral from 0 to root 3 and hopefully show that we get this, because then all we've got to do at the end is subtract that part. Right, let's put this together then. So what we've done so far. I mean, I've done part of part B. So C above. Okay, now area R. Just trying to decide. Remember, is it called the shaded region? So area of R is equal to the integral from 0 to root 3 of the function y differentiated with respect to x, and I'm going to minus this thing here. this area of the triangle that I had before. So let me focus on the integral. Well, first of all, I'm not going to integrate with respect to x. These are functions that in terms of t. I need to change it into a parametric differentiation. So what I can do is write y, and then it's going to be times dx by dt, and integrate with respect to t. I've essentially used a chain rule here. This is equivalent to dx. And then I'm going to integrate. Remember, it was at pi over 3 that the value of t was for this point. I just need to look at where what the value of t is when x is 0. We can see that if x is 0, sine t is 0, so it's going to be that t is equal to 0 on this interval. Okay, so that's our next bit. Now, remember that y was equal to ln sec t, or minus ln cos t. I'm going to stick with that. And then I'm timesing by dx by dt, which we calculated as 2 cos t. The thing that jumps out at me here is that we have a product of functions. I don't think a substitution is going to help. So we need to use integration by parts. Now we've already, you don't really want to be trying to integrate the log of something. So we've already actually differentiated it. So that one's going to be u. And remember, when we found dy by dt, we got that it was tan t. You can look back at your notes to see that. And then this can be v dash. So v is going to be 2 sine t. Now I've gone straight for using the limits. You could ignore that and put them in at the end. Sometimes it depends how complicated an integral is as to whether I do that. So it's going to be tan t and then 2 cos t, oh sorry, 2 sine t. And I'll bring this 2 out here. I don't know why I just did that, to be honest. Sorry, I kind of rushed. Let me kind of just, I've started writing the integration by parts formula, and then I just carried on and actually substituted in. Apologies. So I'm actually minusing the integral from 0 to pi over 3 of u dash v. Okay, then let's put this next step in. So it's going to be minus ln cos t times 2 sine t evaluated between 0 and pi over 3. And then it's going to be tan t times 2 sine t. Now what we can do, I'm going to do that here. I'm going to bring the 2 out. You can just carry the constant through. I've got another integral to deal with. Before I deal with that, I'm just going to substitute in. So I'm going to get, and actually I'm just going to grab what the actual answer is, because, you know, it helps just remind ourselves where we're actually trying to get to. So we get minus ln cos pi over 3, which remember was a half, times 2 sine pi over 3, which is root 3 over 2. And then when I put 0 in, I'm going to be timesing by 0, so I don't have to worry about that. These two are going to cancel. And then you can see in the answer there's a ln 2, so I'm going to bring this back in, and we're going to get root 3 ln 2. So this is looking quite good because I've got my root 3 ln 2, so basically I got this term. I know I got another two terms to deal with, but I have another integration by parts to deal with, and that will give me two terms. Hopefully. So I'm just gonna over here, I'm gonna do this integral tan t times sine t. Forget about the two, forget about the limits. This can be u and this can be v dash, because it's just you get like quite a nice answer when you um, differentiate tan. You just get sec squared. These are all things that you're like expected to just know off the top of your head for this sort of question at the pace we need to work at. And then v will be minus cos t. So we'll get minus tan t cos t, u times v, minus sec squared t times minus cos t, and change that to a plus. Now sec squared t is 1 over cos, so actually that cos is going to cancel with that 2 there. So you've got to be aware of that. And then tan t times cos t, well tan t is sine over cos, so actually the cos and the divided by cos are going to cancel, and this will become simply sine t here. So we're nearly there. I'm just going to write down that this is equal to, I'm just going to minus sine t plus the integral of sec t. Now this is an awkward one, but it's one that you should, if you practice enough, you can start to, just be able to identify. And this one is actually ln sec t plus tan t. There would also be a plus c, but we're going to be doing a definite integral, so I'm not going to worry about that. Now, to show that this is true, it's really tricky, and you kind of almost need to know the answer to actually get to this. You have to times top and bottom by sec t plus tan t, do a substitution, and it will come out. But basically, just learn this one so you can identify it. And we're nearly done. So that means the original integral, which I'll call star. It's a bit right back here. Here. It's going to equal that root 3 ln 2 that we had. And then I'm minusing two lots of this thing, but evaluated, I can put it all together, in fact, because I have these two things finished. It's going to be minus sine t plus ln sec t plus tan t in modulus. Now, I just want to remind you, maybe I should have made this clear at the start of the lesson. Yeah, just make sure you have these ready. It's the same as sine 60, so that one is root 3 over 2. Cos pi over 3 is a half. And tan pi over 3. If you can't remember that one, you can actually just divide them, but it's root 3. Now, I've got like a double negative going on. So what I'm going to do is I'm going to change this to a plus and get rid of that negative, and then change this to a minus. They're the same thing. Plus 2 lots of sine pi over 3 minus ln. Now sec pi over 3 will be 1 over this, so it will be 2. And then tan pi over 3 is root 3. The only thing I've got to do is I have to substitute 0 in, but I don't get any contribution here. And here I get ln 1, so I also don't get a contribution. Okay, these are going to, when I multiply the bracket, I'll just get root 3 and then minus 2 ln 2 plus root 3. We're nearly there. As you can see, that's what we wanted to get, and you can see that's what we have actually got. I just need to factorize out that root 3. And I don't need the modulus sign because it's positive. Hence, area of R, we're nearly there, it's going to equal this integral that we've just calculated and then I just need to minus that triangle that I had before. I think, yeah, there it is. Because we've done this bit, we just need to minus that the blue triangle to get it. So root 3 over 6 ln 2 squared. And that's our answer. Just to remind you, that was the triangle. And like all of this stuff was the integral. Okay, really neat question. This is the answer in exact form. We can't do anything else with that. It's really tested us on a lot of stuff. Parametric differentiation and integration, tangents, and then the hardest bit by far is doing the integrals here, the actual parametric integral, but it's not really the parametric integral itself, it's when you get to this, having to do integration by parts, then by parts again, and even after that we get the have to deal with ln sec t. But we're there. Good question, well done.